This is Physics 140, the best way to begin your day. Today we are doing problem number 1332 on computation of gravitational force. A thin uniform rod has length L and mass m. A small uniform sphere of mass small m is placed at distance x from one end of the rod along the axis of the rod. The problem we are doing today is to calculate gravitational interaction force between the rod and this small mass, which we can treat as a point mass. Okay? All right. So that's the problem. Let me draw a picture. So the picture is, so we have a rod and a point mass. Okay, and we are given the mass of the rod, we are given the length of the rod, and we are given the mass of the point mass. One note to make before we proceed with this problem is that we cannot approximate the rod as some kind of point mass placed at the center of mass of that rod. We will see that from our result that the result will be different compared to the result of interaction of a point mass m and another point mass capital M placed at the location at the center of mass of the rod, even though the rod is uniform. The simple explanation is that the right end of the rod has a much stronger force acting on it or providing a force on the point mass compared to the left end. The contributions of the right end and the left end are not comparable, they're not equivalent, because the right end is so much closer to the point mass compared to the left end. What we can do, however, we can always write how two point masses interact. We don't know how rods interact, we don't know how, say, triangles interact or rectangles interact or some other funny shapes interact, but we do know how point masses interact. So the idea is, as with many integration problems, is to split a shape of interest, in this case rod, into tiny bits, point-like masses, and consider interaction of these point-like masses with the mass of interest. For example, if I call this mass dm, a small mass dm, I know how to write interaction between that small piece of rod with my point mass, small m, and then I would just need to sum the contributions from all the small masses along the rod, and to get the overall force acting on the point mass, small m. Alright, so what is this force? We know what this force is. This is attractive force, so this small bead pulls with force dF on the point mass, and the magnitude of that force is given by the Newton's law, universal law of gravitation, which is g, one mass, the other mass, over the distance between the two masses squared. Right. Notice the distance is this distance between mass m and mass dm. So if I introduce axis r, then the point mass is going to be at the origin, and mass dm is going to be a distance r. We can also say that the right end of the rod is going to be the distance x. That's what we are given. This distance is x, and the left end would be the distance x plus l. X plus L. Alright, so that's the force provided by this bead. The overall force provided by all beads of mass within this rod, it would be simply the sum of contributions from each bead. So we can write, it's the sum of all these contributions. Integral is the sum of all these contributions. We can write this in this form for this geometry because all beads are pulling on the point mass towards the left. So all these df's due to all beads within the rod are directed leftward. So all, all of these contributions are pointing towards the left. So all of them in the same direction. So we can say in this particular situation that the magnitude of the total force is simply equal to the sum of the magnitudes of individual small contributions. Of course, in general, we would have to sum it as vectors. We have to sum these contributions as vectors. But in this case, since all these contributions are well in the same direction, we can sum them as magnitudes. Okay? Alright, so well, these integrals, therefore, well, we know what df is simply gm dm over r squared. And certainly, since g and m are constants, we can pull those constants out, but we cannot pull out anything else. Why? Well, because r is different for all beats, so if you choose a different beat, it will be a different r. Well, so at different locations along the road will correspond to different value of r. So, well, that's a variable, that's a quantity which changes with location. So the idea is now is to compute this integral. In essence, the physics part is done, right? So the physics part is to write this integral, and the rest is just how we compute this integral, how we practically compute this integral. Well, in order to compute this integral, we either need to express m in terms of r, or r in terms of m, so that both our function and our variable are the same. Right? We can do the integral of f of x dx, but we cannot do an integral of f of r dm. Okay? So it's either m in terms of r or r in terms of m. In most problems, it's typically easier to express mass or any other quantities in terms of some coordinate, well, because it's simply just easier direction. Okay? So let's try to express m in terms of r. So how do we do that? Well, in essence, we need to relate increase in mass or the mass of this beat to the variation of r as you go from one beat to another. Right? So if you go from one beat to another beat, to the adjacent beat, your r increases from r to r plus dr, right? Where dr is the increase. Or you can say, well, it increases precisely by the thickness of this beat. Right? So essentially the increase of the coordinate as you go from one beat to the next beat is precisely equal to the width of this beat. So what we are trying to do in this situation, we are trying to express dm in terms of dr. Okay, that's the idea. Alright, so well, in this case, this task is particularly simple because the problem tells us that the rod is uniform. So that means the linear density of the rod, which is mass per unit length, is constant and is simply equal to the total mass divided by the total length. Total mass divided by the total length. Well, that's linear density, mass per unit length. So if we know the length of this bit of mass, the shaded piece of mass, we can say what its mass is. It's simply, well, density, mass per unit length, times its length. So in this situation, it's just m over l times dr. That's the relationship we see. Well, another way to obtain a similar relationship is to use, again, uniformity of the rod and to say, well, for example, if there is 1% of length in this shaded portion, that means that there must be 1% of mass within that shaded portion, right? So the fraction of length should be equal to the fraction of mass. We can mathematically write this as dm over total mass, fraction of mass within the shaded portion, must be the same as the fraction of length, dr over the total length. Length of this portion divided by the total length. Well, from this relationship, we still get exactly the same result, which is m over l dr. So one way in terms of density, or the other way in terms of these fractions, we still get the same relationship that mass, well, is proportional to the length. So the longer the beat you select, well, the more mass you get. Okay. Alright, so well, now we can write the force in terms of only r variables. So the total force acting on the point mass is g m integral, well, dm is m over l dr over r squared. So we can pull m over l outside the integral because these are constants now, gm, capital M over l. And the integral we actually need to compute is simply dr over r squared. Now the integration limits can be read directly from the picture. Well, the lowest value of r corresponds to the right end of the rod, and here r is equal to x. R is equal to x at the lowest value, and the largest value of r corresponds to the left end, and here the distance between the left end and the point mass is x plus l, so the largest value is x plus l. X plus l. Well, this is certainly the integral we can do. Well, integral of 1 over r squared is minus 1 over r, so it's g m over l minus 1 over r, taken between r equal x and r equal x plus l. Well, let's now plug these values in. G m over l minus 1 over x plus l at the upper limit, minus minus, which is plus 1 over x at the lower limit. Okay? Now let's simplify this result a little bit. So, well, let's bring this to the common denominator. The common denominator would be x times x plus l. So g m over l. Well, x times x plus l. So we would need to multiply the first fraction by x. We would get minus x. And we would need to multiply the second fraction, numerator and denominator, by x plus l. So the contribution would be x plus l from the second term. Okay? Now this can be simplified even further. Minus x plus x cancel out, and we are left with g m, capital M, l in the numerator, divided by l, x plus l. Well, l also cancels, and our final result for the interaction, for the gravitational force, is g m over x times x plus l. That's the result. That's how strongly the rod attracts the point mass. Well, that's the force. It is always worth checking if the result makes sense. Well, first of all, units are correct, right? The units of the force are indeed the same as for, well, the universal law of gravity. G, one mass, another mass, some length squared, right? So this has units of meters, this has units of meters, so it's meters squared, okay? Now we can also check what this result reduces to if x is very large. Well, if we take this point mass very far away, x becomes very large, while L becomes small compared to the distance of the point mass, and while we can essentially neglect L compared to X if X is much larger than L. So what happens then? Well, if we do so, well, the quantity in brackets can be just viewed as just X, if X is really much bigger than L, and the entire denominator becomes X squared. X times x. So our result reduces to gmm over x squared, exactly the same result we would get for 2 point masses x apart, which does make sense, right? If you take the rod far away and the rod is really, has small dimensions compared to all the distances involved, this rod from far away looks like a point mass. So the interaction of this rod with another point mass should follow roughly the same dependence, right? So it should look like interaction of 2 point masses regardless of L. And that's exactly the result we get in the case of x being much larger than L. So yes, our result does reduce to the proper limit when x is much greater than L, which is another checkpoint. Alright, so we'll continue with another problem later on.